Hey there. Okay, so we really dug deep into the mechanism of resistor networks, very complicated systems of resistors. We won't be doing that with the capacitors, so I don't want to go so deep into it, but you do need to know the method. It's really almost the same exact thing, except for instead of using Ohm's law, you use the definition of a capacitor. So I'll show you that. But also there's a few principles that you have to know. And then there's some equations that you have to know. So let's look at our first equation. If we have another circuit, but in this case, instead of attaching resistors to it, we attach capacitors. If we make all of them the same, then we're going to get a different effect than we did with the resistors, and the equations are going to reflect that. So if we have 10 microfarad here, 10 microfarad here, 10 microfarad here, the effect, the net effect here, is that since we don't get charge flowing through the capacitors, instead we get them flowing onto the capacitors. What we get is, if this piece right here is overall neutral, then the total charge on each of these plates, I'm going to go ahead and make this one positive, and this positive, and this positive. I'll use blue for negative here. Negative, negative, negative. This negative and this positive have to be the same, because this is just a dead piece of wire that just happens to be connected to capacitors, right? It has no ability for charge to flow off of it, so that means whatever the charge is on this one is also the charge on this one, is also the charge on this one. So you can equate it sort of to what we were doing before, where resistors in series will have the same current. Capacitors in series will have the same charge, right? It should still make sense that because each of these is connected to the same voltage source, that each of them has the same voltage across them, very much similarly to the way we had with the resistors, right? Okay, now what about the equations? Well, it turns out they're the opposite. If you want the equivalent capacitance for a set of capacitors that are put in series, it turns out you're going to have to do the opposite of what you did with the resistors. So it's a little easier to remember because you don't have to worry about coming up with new equations. You just reverse the ones you had in the resistor case. Parallel capacitors are going to have an equivalent capacitance that is simply the addition or the sum of the individual capacitors. It's absolutely the opposite of the resistors. So how do we find stuff on here? Well, let's do a simple one so that we'll get a general concept here. Remember our rules. So once you've got that down, then it's not so hard to figure out the rest. After you've practiced the other type, when you've practiced the resistors, then you basically have the hang of the strategies, right? So we've got a 12-volt battery and a capacitor here with a capacitance of 5 microfarad, and then another capacitor with a capacitance of 20 microfarad, and another capacitor with a capacitance of 10 microfarad. Okay, and that's going to be our circuit. Okay, I know we call it circuit even though the charge only flows up to the capacitor, but we have reasons for doing that. Okay. So how do we solve this? Well, it's the same principle. We find something that's either entirely in series and entirely in parallel. These two are entirely in parallels, and it's not even hard to add parallels when you're dealing with capacitors. All it is simple addition, right? Okay, so we'll create an equivalent capacitance here. Here is our 5 microfarad, and this is simply 30 microfarad. Okay, then we go through the process of combining our series capacitors into one single capacitor. This equivalent capacitor is going to be the reciprocal of 1 over 5 microfarad plus 1 over 30 microfarad. Don't forget to put the little reciprocal mark on there, because if you don't put that on there, then you might forget to flip it afterward, right? This is the same as saying 1 over this is equal to everything in the parentheses. So, okay, so that gives us then, I like fractions like I've said before, so that gives us, let's see, 6 over 30 plus 1 over 30, 7 over 30, flip it, and you get 30 over 7. Not a very clean fraction. My apologies. But that's okay. It's 4... I gave up 4.29. I didn't have faith in myself. Alright, and that's going to be, of course, in microfarad. Okay, so if we have 4.29 microfarad as the total charge, we can go through our same process of, and this 12-volt battery, of finding extra information. We might want to know, let's say, what is the charge on the 5 microfarad capacitor? Okay, now I didn't need to ask a question up until now. My entire objective this whole time was to simplify the circuit until I got one single capacitor to represent the entire thing. Now, if I have questions, I can begin answering them, right? Okay, let's put that down as a question. What is the charge on the 5 microfarad capacitor? 4.29 microfarad is the total capacitance on the circuit. What's the total charge on the circuit? The total charge on the circuit has got to be equal to, according to the law of capacitance, C times the voltage of the entire. So the entire charge, the entire capacitance, the entire voltage. That's for this circuit, right? Okay, that's going to equal... Give myself some room there. 4.29 times 10 to the negative 6 farad times 12 volts. And that's a 51.4 microcoulombs of charge. Okay, that's on the entire thing, right? Okay, so let's take a step back and look at now our next, or previous, I guess would be another way to look at that, circuit, right? Or equivalent circuit. And what do we know about that? We know that the charge on this one and the charge on this one are equal. And in fact, if the charge on this plate is equal to the charge, the opposite of the charge on this plate, then that's the same as the charge on this plate and the charge on this plate. So in fact, we know that this contains a charge of 51.4 microcoulombs, and this contains a charge of 51.4 microcoulombs. Interesting. If we wanted the voltage across the 5 microfarad capacitor, then all we have to do is use the capacitance that we know and the charge that we now know also, and we have it. We use the same equation but with different subscripts. So we know that the voltage across the 5 microfarad capacitor is going to be the charge on the 5 microfarad capacitor divided by the capacitance of the 5 microfarad capacitor, or 5 microfarads, right? So that doesn't make it too terribly difficult. And that micros will cancel there so that we have volts as our unit. And we get 10.3 volts, which is almost all 12 volts. Why would almost all the voltage be piled on this tiny capacitor when we've got a 30 microfarad capacitor right here? Well, what we're really doing is saying, remember, the voltage has to do with energy, right? It has to do with how much work it takes to make stuff happen in the charge world. So, in other words, we've got this nice, happy bucket that's easy to store charge on, and we've got this kind of sad, little pathetic bucket here that is not very easy to store charge on. And if we're going to pile 51.4 microcoulombs on both of them, well, we have to work a lot harder to get that charge on the 5 microfarad one. So, the battery spends most of its voltage applying charge to the 5 microfarad and not as much to the 30 microfarad. Okay, hopefully this kind of mirrors the process of the resistors. Sum for the series resistance, whereas for capacitors we have straight sum for the parallel capacitances. And then for the resistor systems we had the same current for series, whereas in the capacitors we have the same charge for series. For the resistors in parallel we had the same voltage, and also in capacitor case we have same voltage for parallels. So that once you've got those rules down, this is just logic and fun. So, okay, enjoy.